So, good evening, everyone. I'm very happy that we have already 50 R enthusiasts here. Please say hi and mention from where you're from. We are so extremely happy that we have such an audience. Okay, so let's go forward. It's my pleasure today to introduce Erin LeDell, co-founder of Our Ladies Global and Women in Data Science and Machine Learning. Erin is also an academician turned academic turned leading chief scientist in H2O.ai. We are extremely happy to have her here because we want, as our foundation, why our foundation want to point not only people who achieved a lot in the field of machine learning data science, but of course, it counts too, but also role models. And Erin did a lot of great efforts for promotion of diversity in our community. So I'm clapping as a surrogate audience, and Erin, the floor is yours.
Thank you. Thanks for having me. So I guess I will share my screen. Okay, let's see. Okay, let me make this bigger. Okay. Okay, I'm assuming that everything's working with my slide share. So thanks for having me today. It's I always love to speak to an R audience. So I appreciate you inviting me to give a talk today. So today I'm going to talk about something that I talk about a lot lately, which is scalable automatic machine learning in R with the H2O library. Okay, so let me tell you a little bit about what I'm going to talk about for the next 40 minutes, and then we'll have about 20 minutes for questions and discussion afterwards. So first, I'm going to tell you a little bit just about the H2O platform. So we use the word platform, I guess, instead of library, because it's not just algorithm implementations, it's also sort of a whole distributed computing platform. And so that's one reason that we use that term. But primarily what it includes is machine learning algorithms that we have written from scratch in a distributed fashion so that they can be run across all the cores on a single machine or across multiple machines in kind of a multi-node cluster scenario. And it was really from the beginning designed for big data. That was the whole point of writing the library, because there are certainly other machine learning libraries that exist out there in R and Python that have a bunch of machine learning algorithms. So that's kind of one of the unique components about H2O, is that it really was designed to scale to big data sets and to be fast. The algorithms themselves are written in Java, but probably everybody on this webinar and most data scientists are not Java programmers. Most data scientists either use R or Python. So, and this is a library designed really it's designed for engineers and data scientists, but primarily data scientists. So we have APIs in R and Python. And because it's written in Java, it's very easy to have a Scala wrapper as well. And we also have a web GUI. So if you're not even a programmer, or maybe you just, don't want to write code all the time, the same code over and over again, you can just click around through the web GUI to train models. And then one of the other unique features about the H2O library is that there's basically a lot of times what happens in industrial settings when you're, prototyping things, you might write something in R or Python, and then if you want to productionize that code, you might hand over your code to another team, like a team of engineers who would rewrite everything in Java or C++ or Go or something like that. And there's kind of this disconnect between the data scientists and the engineering and the production of the models. So one of the things that's nice about H2O, especially for data scientists, is that you don't need somebody to rewrite any of your code to be able to deploy your models. Even though you're using R and Python to write your code in H2O, the models can be deployed or exported as pure Java code, which can be then integrated into a Java application, or it could be made into a REST API. For R people, if you still even dealing with productionizing Java code maybe is not that appealing. So you can also use like the Plumber package. There's a handful of blog posts that will show you how to use H2O and the Plumber package to deploy models if you don't want to mess around with any Java. So there's a lot of different options for that. We have a couple different ways you can save the models too. You don't have to, you can just save them to disk and load them back in. That's kind of the non-production way of doing that. So that's also an option. And then because this was, H2O was started back in 2012, and I think the first version of H2O came out in 2013. Back then, the big thing that everybody was talking about was Hadoop. And so one of the other sort of initial inspirations for H2O was to have a machine learning library on top of Hadoop. So that's maybe not necessarily how a lot of people are using it now, but it works seamlessly with Hadoop and then also Spark if you have your data like in a big data platform. But what we see a lot of people just doing is just using it on their laptop like a normal library. So you don't need to interact with any of these big data systems unless you have to, basically. There's no need to complicate things if you don't need to use Hadoop or Spark. So if you just want to run it on your laptop, that's totally fine. Okay, so that's just kind of some background. Then I'll say one more thing about the distributed computing part. So just so you know, because we have a couple different terms that we use in H2O that you should know about. So one is the H2O cluster. And so that's just the name that we call the process, the Java process, basically, where all of the computation is happening. That's where your data lives. That's where all your models are trained. It's basically just memory that can be shared across multiple machines if you're using a multi-node cluster. So that's just, it's just a fancy term for a process running on your machine where all of the stuff is happening. So you're not actually doing any computation in R. You're actually doing it in Java using an R API or a Python API. And then the other thing that I should mention is there's something called an H2O frame, which is basically just a data frame. And so when you're using H2O in R, you treat an H2O frame as if it's a data frame, and you just kind of pretend it is, and then it acts like a data frame in most cases. All of the base R, well, I shouldn't say all of it, but pretty much, if you have an H2O frame, you can use any kind of base R functionality to manipulate the frame. That you would write the same exact code to, subset rows or look at columns of an H2O frame as you would a data frame. So we don't want you to have to learn a whole other way of interacting with a data frame. So that's what we have. And what's unique about it is that if you're using a distributed system, let's say you have a multi-node cluster, then some of the rows in that frame will be on one node and some of the rows will be on another node, and it's split up row-wise. But when you interact with the frame, you don't need to know that. That's just some background. So this is all, all I'll say about distributed computing. It's not really that important to know about, but it's useful, I think, just to have the terminology. Okay, so what do we have in the H2O library? So it's a whole bunch of different things. We have supervised and unsupervised machine learning algorithms. So things like gradient boosting machines, random forests, deep neural networks, GLMs, stacked ensembles. There's actually quite a few more available, but I'm not going to list them all. But there's, at the end of the talk, I'll point you to some resources. The H2O user guide is the main place that you would want to go visit online to learn about how to use H2O, and that will list all the algorithms that we have as well. Some of the other things that I like about the library are when you're doing machine learning, there's a lot of data pre-processing sometimes that you need to do before you can do any kind of training. So, and that just really depends on the software that you're using. It depends on the algorithm that you're using, but it also depends on the software and how much effort has been put into dealing with that automatically. And actually most machine learning software doesn't do any data pre-processing automatically. They kind of expect you, and maybe, in a way there's some benefits to being explicit about what's happening. It requires you to write a single line of code for everything that you're doing. If you're one-hot encoding the categoricals, or if you're label encoding the categoricals, or normalizing the variables, you'll see code written out, and it will be very explicit that that's happening. But that's also a lot of extra code to write when you know that you have to do this every single time you use an algorithm. So that's something that we do automatically. So if you have data where in your data frame, some of the values are missing, or we'll fill them in automatically. The big one, I think, for me is like if you have categorical data, you don't have to do anything with it. So if you have a factor column representing some kind of categories, you can just pass that along to an H2O algorithm, and it will do whatever it needs to do to make that work for machine learning. So it depends on which algorithm you're using, what will happen underneath. So in the case of a GLM or a deep neural network, it will do automatic one-hot encoding. For the tree-based models, it won't need to do that because in H2O we have implemented a group split technique in the trees, which means that it can handle categorical variables natively. So this is all just stuff to make it kind of easier to do machine learning. Another thing I'll mention is for all the algorithms, we have something that's called early stopping. So most algorithms have some kind of concept of, at least especially in H2O, how we've implemented it, some kind of concept of incremental training. So with tree algorithms, like the most obvious thing is like in a gradient boosting machine, you add trees and that's how you train the algorithm. So, and those in particular are easy to overfit. If you keep adding too many trees, it'll start to overfit and then you'll start to lose performance. So one of the things that you generally have to do when you're training, in particular a gradient boosting machine, is to figure out when to stop training. So we have some built-in features to do that. Of course, you can override that or tweak that. We can make it more sensitive or less sensitive to early stopping. But we try to have some defaults in there that make it easy so that you don't kind of shoot yourself in the foot, basically. So it should stop at like a decent time. Maybe you could train a little bit more or less if you want to tweak it. But yeah, so we have stuff like that. And then once you've trained the models, I shouldn't say once you train the models. So the next bullet point is actually about training and sort of utilities around that. So, we might want to do cross-validation, so it's easy to do that in H2O. There's just an n-folds argument in every function. You just set that to some number, and if you set n-folds equal to 5, it will just do 5-fold cross-validation for you. So there's literally no code to be written. It's just a number you pass along. And also there's a nice interface for grid search and random search. So it's pretty easy you basically just have a list of the parameters that you want to tune over and then the ranges, and then we'll train a grid or a random search. And so there's nice utilities for that. And then once you have the models trained, all the models have some concept of variable importance. And so One of the other things about H2O, just like all machine learning libraries where they have kind of a unified interface to a bunch of algorithms. So, you would extract the variable importance the same way from a random forest as you would from a GLM or a deep neural network. There's just a function for that. So it makes it really easy to test things out and to reuse code, that you're using to train one algorithm versus another. Every algorithm has model evaluation metrics, like AUC, mean squared error, etc. And then there's lots of different plotting methods. And something I don't have on here is there is also starting to be more and more interpretability functions and functionality that you can use afterwards as well. So that's kind of just an overview of H2O. So I'm going to try to move on quickly to what is Auto ML. So this is kind of my explanation of what I think some of the goals or features of Auto ML is. So you could say probably the main goal in Auto ML is to get a good model with the least amount of time or effort. So there's kind of two places that people spend a lot of time when they're doing machine learning. One is just writing all the code to do the thing that you're trying to do, whether that's training a grid search or training a bunch of models. Just writing that code takes a lot of time. So there's that. And then there's the actual amount of time that you're actually training the model. So once you've press go, you have to wait for the model to train. So we want to minimize both of those things. So it's easy to minimize the code. All we do is just wrap everything in just a simple function and then hide all of the work from the user, so that all you really have to think about is what is your data, what are you trying to predict, and how are you going to measure that? Like, what model metric are you interested in? And then how long do you want it to train for? So most, I would say almost all AutoML tools, you can train them for some amount of time and then you stop. So you say, I want you to train for 1 hour or 4 hours or whatever it is. So yeah, anyway, so these are some of the goals, I think. So we want to reduce the effort involved. And also, when you reduce machine learning into a simple function, that also hides a lot of the complexity of tuning these algorithms. So that also opens up like high-powered machine learning techniques to people that are new to data science, who basically just know enough about supervised learning to understand the concept. And that's really, every algorithm is really just kind of some black box, and you give it some data, it trains a model, and you evaluate that. They're all kind of doing the same thing. So you can think about AutoML as doing the same thing as well. The other thing is we would like to get better performance overall. So if we can have kind of a baseline function that people could try out anytime they're trying a new machine learning problem, it really helps you get an idea of what's possible on that problem. If you, sometimes what people do, in their process would be, let me just first train a GLM and see like what's sort of the lower bound on what I can do here, or why don't I train a default random forest? There's nothing to tune, and they get kind of some idea about where they're at, and then they can come up with a strategy like, okay, we need to get this higher. What could we do? Should we do more feature engineering? Should we do more tuning? Should we try different models? But if you have an AutoML function, you can kind of get a pretty good sense of what's possible quickly. And not just what's possible on a default algorithm, but just a really strong algorithm. So that's quite helpful. And so also what I think can be very useful is, I think for AutoML, it really opens the door to a lot of other applications of machine learning and research. So sort of applied sciences, I could see people working in that field. They know a little bit about machine learning, but not enough to really do a good job on the problem. So, but that's great, because we can just give them a tool that where you don't really need to know a whole lot about it, and you can get a good baseline for whatever your scientific problem is, and you know, write a paper about it, and not spend too much time focusing on the machine learning part, but rather the unique application of machine learning to some domain. So that's, anyway, that's kind of just an overview. Let me check my time. Okay, so let's see. Here are some different aspects of machine learning in general. So the machine learning process, or the data science process, would involve preparing the data in some way. So that could be feature engineering, that could be just cleaning up the data, removing missing values, things like that. Then, you know, so there's sort of the data aspect, then there's the modeling aspect. So at this point, it's not clear that we could tell in advance what model might work on a given problem. There is research into this area of, there's sort of this concept of, if we have a data set, could we predict which model would be good, or which algorithm would be good with which parameters? I think there is a lot of research in that area, and that could be kind of a future direction. It's not even a future direction, but like, I think that is a direction that automatic machine learning is heading in, is actually predicting the results rather than doing all the training itself. But right now, essentially how most AutoML systems work is that you end up training a bunch of models, and then, you know, to try to find a good one. And once you've generated a bunch of models, one of the other things that you can do then is, if you really do care about the predictive power of, as sort of the main goal, whereas other goals could be, is it interpretable? Is it a fast model that could be used in production? Things like this. But if your main goal is really just model performance, generally, if you could take all or some subset of the models that you've generated and make an ensemble from that, then you're going to get an even stronger model. And so that's why I include that here. Is if one of our main goals with AutoML is to kind of get the best model possible, then we should definitely consider ensembles, because that is one way to get the best model possible. And if you've ever heard of Kaggle.com, which is a data science platform for doing data science competitions, you'll know that ensembles are really the way to get the best performance. Usually all the winners of these Kaggle competitions are winning using some type of ensemble. Okay, so this just says a little bit more detail about what each of these topics covers. So for data pre-processing, it could be a lot of different things. One thing that's maybe a little bit overlooked, but is super important, is how do you process your categorical features? Because that's generally where, if you don't do much, you're kind of leaving a lot of I don't know, stuff on the table. Like there's a lot of stuff you can do with categorical features to get better models at the end. And it has a lot to do with how you process them, and has to do with the cardinality of the features. And you could actually also really shoot yourself in the foot, because if you have some features that have a very high number of categories, and you hand that over to a machine learning algorithm, in most cases, that's not going to be good. It's going to blow up the memory. It's going to be a bad situation for you. And so you need to do some work on the front end to make that better for when you do the machine learning. So that's something to think about. And for model generation, probably the thing that people are the most familiar with is a grid search. Just a typical grid search or a random search. That's just, you know, trying a whole bunch of things and seeing what works. There's also more complex techniques, such as Bayesian hyperparameter optimization. That's an iterative method that you can do it in serial. You have to basically train a model, and then you have this sort of surrogate model that is advising you about which parameter values to try next, and then you try them, and then you report back to the surrogate model, and it will give you a new set. And it's kind of this feedback loop. and then you get closer and closer generally to a good solution. So that's a different approach, and also quite widely used. For ensembles, I think probably the two most popular techniques are stacking or stacked ensembles, and then something called ensemble selection. And I won't go into a whole lot of detail about that, but just know that there's a couple different techniques for doing ensembles, and yeah, they have pros and cons to each one. Okay, so AutoML, if you're new to AutoML and you're just kind of not sure about what's out there, what are the types of AutoML, what does the word AutoML mean? You know, is it the name of a piece of software? Is it a thing? What is it? So I wrote this blog post that can help, I don't know, if you're new to AutoML or you want to introduce a friend, you can read this blog post, and it will talk about the different software tools that exist. The date on this blog post is now August 15th, 2018. It is starting to be a little bit out of date. I should probably write a newer version, because there have been a few new tools that have come out since I wrote this. But it'll give you a general overview about the types of AutoML. The main differentiator in the different types of AutoML, I think, has to do with, are you doing deep learning or image classification or some more complex data, or are you doing tabular data? So I'm going to focus on tabular data. That's what H2O AutoML does. And that's what we're going to talk about. Okay, so let's see, we have about 10 minutes. So let me tell you about H2O AutoML. Okay, so this is the same slide here. And this is a highlighted, what I have highlighted here is what we currently have. And I'm seeing that it says version 328. We just released version 330, I think about a week ago. So the list hasn't changed actually, but I'm just noting the version number is slightly outdated. But so for H2O AutoML, we do the basic stuff that we always do in H2O. So that would be imputation, one-hot encoding, standardization, stuff that we get for free just because we're using H2O. Something that we have in development is something called target encoding, which is a nice way to encode your categorical features. You can do that inside of the H2O platform already, outside of the AutoML algorithm, but what we're working on right now is trying to do that in an automated fashion. That's been a long project. Hopefully it will be wrapped up soon, but that's one of the things I'm excited about right now in development is getting that automatic feature processing. And then for model generation, we use random search so a combination of random search and stacked ensembles. And I'll explain on the next slide, or one of the next slides, like how that works together. So those two things work quite well together. So let's talk about that. So why do we do this? So these, the thing about stacked ensembles is that they work well if the base models that are inside of the ensembles are generally, strong models, and also that they make uncorrelated errors. And what that means is that, they fail in different ways. So when one algorithm is failing, we hope that another one in the ensemble is able to do a better job on that particular data point. So, so one way to get models that make uncorrelated errors is if they're sort of diverse among themselves. So you could have different algorithms, you can have very different settings within each algorithm. So if you think about what random search does, it's really just generating a quite diverse range of models because there's no restrictions. I mean, we do actually have restrictions about what we search over, like which hyperparameters and which ranges inside of AutoML, but generally, you're randomly sampling these things. So it's a really good way to get a diverse set of base models that can then be used to train the stacked ensemble. So we have found that this technique of these two things together works just as well as other, what people might consider to be more sophisticated techniques like Bayesian optimization. So it also helps that H2O is a very fast system. So all the algorithms are quite fast, which means that we can do this quickly and we can train a lot of models in a short amount of time and then stack them together and get good results. So this is a little bit of an overview of what is the algorithm. So I've said it does some basic data pre-processing, and we're working on adding some more stuff. Then it trains random grids of basically most of the supervised machine learning algorithms that we have in H2O. So we get a very diverse set. And we restrict what the hyperparameter space is. So, you know, anytime you're doing a grid search or a random search, you do have to say which hyperparameters are you going to tune and what are the ranges, and then you randomly sample in there. And then we train two stacked ensembles. So one is trained from all the models that were trained during the AutoML run. And we call that the all models ensemble. And, you know, we don't know how long people are going to run this. Are they going to run it for an hour, you know, a day? Is it going to be 20 models or 5 models or 300 models? We don't know. So the all models ensemble could be quite large if you run it for a long time. So what we also wanted to do was create more of a lightweight ensemble that's always guaranteed to be small and a little bit faster in production. So we take the best model from each algorithm group, and then we make a little baby ensemble, which is lightweight. That's kind of the one, like if you're gonna take an ensemble to production, we would recommend that. The performance is a little bit less usually than the all models ensemble, but it's still quite good compared to the base or the top base learner. So there'll be kind of a jump in performance from the top base learner to the ensembles, and then there'll be like a little difference between the all models and the best in family. Of course, that's I'm just speaking generally, completely depends on your data set, and you might not get that result, but we see that that's kind of generally what happens. And then what you get as a sort of result of your AutoML run is what we call a leaderboard. And I'll show you what a leaderboard looks like. Okay, so here's the code in R. So it's very simple. It's one function. So the first thing that you do in any H2O script is you initialize the H2O cluster. So we have a function that's called H2O.init. And then we have our little import file function, which is essentially like a read CSV type thing, except for it reads in parallel from disk straight into the H2O cluster. It doesn't go into the R memory whatsoever. So when you have that object called train, that's really just a pointer. It's an H2O frame, or it's a pointer to an H2O frame. And you treat it as if it's a normal R data frame, but it's not. So, and then the interface is I guess it's unique, but it's very similar to all other modeling, you know, functionality in R, where you specify what your data set is, and then in our case we have an X and a Y variable. Rather than passing in Y as a column and X as a matrix or data frame, we actually use those arguments to specify just the column names inside of the H2O frame. So Y is just either a column index or a name of the column. What you don't see here is we have an argument X. If X will allow you to subset the column. So if you want to ignore some columns in your data frame, like if you have an ID column or a date column that you don't want, you can specify X as some subset of the columns. If you don't specify X, it'll just assume everything that's not the response is something you want to use to train. And then you put the time limit here. So this would be running for 10 minutes. Once it's done, you'll get your leaderboard. And here's just a real quick snapshot of what this looks like in the GUI. So same thing, you just click around, no code. This is what a leaderboard looks like. So a leaderboard is a data frame, and in the data frame, the first column is the model ID. So this is not going to tell you all the hyperparameters or anything else. We don't want to clutter the leaderboard too much, so we just have a unique identifier for each model. these unique identifiers in H2O, you can name your model whatever you want. You can give it any kind of ID. Within the AutoML function, we just generally name them with something that identifies what algorithm it is, and then some other info that's helpful to keep track of. So here what we see is this is a real leaderboard for a binary classification problem. And we see a stacked ensemble, all models at the top. We see a best of family in second place, and then we jump down a little bit in performance, and then we see the top base model, which is an XGBoost model. And if you're wondering why XGBoost is here, it's because XGBoost is offered in H2O. So what we do is we wrap the original XGBoost software and we distribute that within H2O. So there's a function called H2O.XGBoost. So if you want to use XGBoost and you want to use it with other models like H2O models, if you want to do ensembles with XGBoost, it's nice to have that inside of H2O so we can use it. Generally, what we see is that those types of models do really well in AutoML. Then we're followed in the leaderboard here by some GBMs. Those are the H2O GBMs. Then we've got a distributed random forest, DRF. We've got an XRT, extremely randomized trees model, which is like a form of random forest. We've got a deep learning model. And at the very bottom, we have a GLM, which is not doing so well, but that's to be expected. So that's an example. I'm going to skip through this section, the pro tips. I'm going to leave this as kind of like if you want to get started and you want to look through and get some tips about how to best use AutoML, you can go through this afterwards. So it's just kind of highlighting some of the other customizations. So you can turn on and off different algorithms in AutoML if you'd like. We'd recommend that you leave them on to start just in case they might do well, but you can turn them on and off. The default runtime is 1 hour. So just some notes about reproducibility. Something that people in R are not used to thinking about probably is memory management. So when you start an H2O cluster, you have to tell it how much memory you want. Well, there's defaults, so it will just give you, you can just do h2o.init and it will start up an H2O cluster. But generally, especially when you are dealing with big data sets and you're thinking about, does this data fit into RAM on my machine? If you're having that kind of thought, you probably want to start thinking about memory. So, just use as much as you can spare, I suppose. So if you have we are actually getting some new information on this about what is good to recommend, especially for AutoML, because XGBoost and H2O do not share memory. So you have to kind of think about both. And so I'm not going to go into the details on that, but just be aware that memory is something that you might need to think about if you're dealing with big data. And another thing you can do is you can train AutoML for a little bit. Like let's say you wanted to just train it for 10 models or 20 models and check and see where you're at. Then you can restart the training. And if you use a seed, you would want to change the seed so you get different models the second time around. But essentially, if you use the same what we call project name, that's an argument in the AutoML function, instead of restarting from scratch, you can just add new models to the leaderboard. So you can kind of pause, check out your results, see how they are, and then start it again. So that's just a tip. Here's a little bit about our roadmap. I'm running out of time, so I'm just going to leave that there. And you might be curious about how does AutoML actually perform like in the real world? Could this replace data scientists? People are always asking if we're trying to get rid of data scientists, and we're not, but we're trying to make them more efficient and give them good tools, just like we give them good tools like, Carrot or Tidy models or H2O or scikit-learn. It's nice to have these tools. They just make data scientists more efficient. So that's how I think about AutoML. It's just like another level of efficiency. So you can just do more with your time. And so this is just a tweet about using AutoML on a Kaggle competition. And what I'm trying to point out here is that if it's kind of a short scenario, like let's say this was a one-day Kaggle competition, AutoML tools actually like were ruling the leaderboard. But if you have like a 3-month competition where humans can be as creative as possible and spend, 2 months on feature engineering, the humans are probably still going to beat all the AutoML tools that we have today. And if you care about benchmarks, I would visit this paper from ICML last year, which compares the open source AutoML frameworks. And if you don't like to read, you can have the paper read to you by Rachel, who used to work at Kaggle. And she had a podcast, or sorry, I guess a webinar, webcast, whatever it is, where she reads papers. Okay, so I'm going to wrap it up. I'm going to leave some links for you if you want to. The first link is the user guide. The next is some just tutorials about how to use AutoML in R. And then we've got like a whole H2O from scratch tutorial that I did for Latin R this year that's also probably of interest to people on this webinar. So I think I have one more slide with just some H2O resources that I'll put up there, and then I'll just leave my contact info and a little shout out to the R ladies. And yeah, and so we have about 20 minutes for questions. So I don't know if I should stop my screen share, or you could let me know.
I think you can stop it. It's about then we can proceed to questions. So first and for all, Erin, thank you very much for your presentation. It was great. And I'm also grateful. I want to express my deepest gratitude to our faithful audience. It's really amazing to see almost 100 spectators from different corners of the world. Especially I'm shouting out to our friends from Africa. It's really great to see you there. And we hope that in future you will be also presenting during our webinars. So Erin, again, thank you for this great talk. And the first question is, of course, and very obvious, would you be able to provide us with the slide deck? Because people in the audience are asking for a slide deck.
Yeah, let me go back to the first, or one of the first slides where there's the link right there. So it's not there yet. I'll put it there, and that link just goes to a repo. I can also give you this slides, and
we'll put the link in the video description, so slides will be available there. Okay, thank you very much. So the next question: there will be very general questions. What is the future of the machine learning field? Do you think that there is a paradigm shift towards the AutoML? We will see more AutoML solutions in future.
Yeah, I do think so. I think especially now that some of the big industrial people like Google, Amazon, etc., are getting involved in AutoML, I think that's going to push it along quite a bit. And I think that once people start using AutoML tools and start to realize that it's not sort of this thing, this mysterious black box that's going to make us not think about what we're doing, I think people will realize that you can actually learn a lot by using an AutoML tool, because it will try things that you never thought to try on your own. So it's actually maybe even a teaching tool for people to help them learn what works and experimenting with things that they've never tried before. So yeah, I do think that just like when I first started machine learning, there really was, I mean, scikit-learn did exist, but it was, I felt like I spent a lot of time playing around with different libraries and trying to get them installed, and like, this one outputs this type of output, this one outputs the other, how do we normalize? Like, I spent a lot of time dealing with lots of different software at the same time. And then it became more of a trend that, and I mentioned this a little bit earlier, that now we have nicer tools, especially in R for doing machine learning. Carrot has been around for a long time, actually, and now we have got tidy models. But I think that this is just kind of, I see it as an extension of that, just making nicer tools nicer wrappers for things. And R really has always been an interface language. I think like there's been a few talks that use R, at least I saw one by John Chambers where he talked about the history of R as just kind of an interface language. And really like, that's what it's all about, is like, how do we make a nice experience and interface to other things that are possibly more complex, and with nice interfaces, we're more efficient. So I think that's where it's headed.
So Erin, another question from our viewer. You showed this very scary slide from the Kaggle competition where where H2O AutoML almost outperformed a lot of contenders. I think it was 6th or 7th, yes, in the competition. So yeah. Our viewer, 8 actually, but it's still a very good achievement. So our spectator is asking, what do you think? Will data scientists in future be replaced by AutoML models? Will the role and the responsibilities of the data scientists change?
I do think it will change a little bit. I think it's always changing, but I think that there'll be just less time spent, at some point it becomes silly to do. And you can think about, if we roll this back one iteration of software development, where you used to pay people to implement algorithms from scratch and then like they would use them. And now that kind of seems like a little bit of a waste of time, since there's lots of software where you can just use it. There's a nice random forest, implementation, or a nice GBM implementation. You can just use it. And so people are comfortable with that transition. And I think it's just going to be the same with AutoML. It's like, you're not going to spend as much time dealing with like setting up grid searches or tweaking or tuning or stuff. I mean, that tends to be, at least in my opinion, like the fun part of data science. So we might actually be automating a little bit of the fun out of it, but hopefully that gives you more time to actually think about other ways to be creative as a data scientist. I think we still have a long way to go when it comes to dealing with data, and automated feature engineering is still pretty a new thing. It's not quite something that we have commodity off-the-shelf tools to do. And I think a lot of focus, and maybe people have noticed this in the last couple of years, has been around interpretability of machine learning models. I think like now that we have tools where we don't have to spend a lot of time tweaking and tuning, we can sort of lift up some of these other things that were maybe not getting as much attention, like model interpretability. And so maybe we'll see more subfields like that growing in popularity, and people thinking about, well, how do we deploy these models? Who is it going to affect? And like, looking at bias inside of a model, things that like we didn't really have time for before. So yeah, I do think it'll change the way that we do things, but I don't think it'll be in a bad way. I think it'll be in like a nice way where, you don't have to worry about so much about like, did I tune that right? Did I try all the different combinations? Should I have tried something else? You'll have some sense of peace around that. You kind of solve that problem. And there's always the case where you can use AutoML as just a baseline, and then you start your process of tweaking and tuning. And if you still want to do all the manual manipulation, you can. So, yeah.
Thank you. So the very last general AutoML questions, next ones will be more tuned to the H2O, but very last general AutoML questions. Do you think that AutoML methods are limited to specific types of the data sets, or AutoML can AutoML deal with all types of data, or do you think it's very limited to a specific type of data?
No, I don't think it is limited. I think like most of the tools right now are for tabular data, but I mentioned that blog post that I wrote at the beginning. Let's see if I can find it. That talks a lot about the different types of data being what gives you different types of methods. So there are tools that do automatic image classification and stuff like that. So I think the trend of automating everything is going to spread everywhere. So I think even though there's not as many tools right now for doing like image classification or NLP type stuff, I think they're also going to get a lot of automation coming up. I think just most of the tools so far have been focused on tabular data.
Okay, so now let's switch to H2O questions. So first one, do you think that with H2O ML, even non-data scientists, but still data savvy, so I suppose with a lot of domain knowledge about the data, can they perform efficient machine learning?
Yeah, I do. I think if you use, even if you don't know how to code, you can use H2O Auto ML through the GUI. So I do think that that's possible. And there are some other tools as well that have more GUI focused things. So, you know, I think as long as you understand some of the assumptions that you're making about the data and you understand what it is that you're trying to predict and how you're going to measure that, I think that's kind of enough to get started. So I do think it's going to open up the doors to a lot more people.
Thank you. So the next one is pretty technical. Will H2O enable automatic forecasting for time series, similar to solutions for regression or classification?
That is a good question. So I know that we have some support for that in a tool that we have called Driverless AI, which is not open source, but it's another H2O, or it's another AutoML tool that we produce at H2O. I know we do support time series stuff in that. In general, H2O doesn't have a big focus on H2O, the open source package, doesn't have a big focus on time series, but I mean, I think I would like to see automation of that if we can come up with it. Generally, how we decide what we're going to work on is a combination of like what we get as priorities from our enterprise support customers and then also from the open source community. So if we have a lot of people asking about time series and automated machine learning for time series, that's, you know, just keep asking about it, because that's how we decide what to work on.
Thank you. And one of our spectators is asking the question that I think we also, a lot of us want to ask: how to select the optimal max runtime?
Well, yeah, that's a good question, because what I have been finding out recently is that, and this is the case in looks like a lot of the AutoML tools, is that sometimes, you know, you run it for longer, you expect the results to get better and better and better. And so sometimes what we see is either it gets, you know, flattened out, it just stops improving, or even in some cases it can get worse. So generally, I think AutoML tools should not get worse as you continue to go on. I think if that's the case, then we need to fix that. But I think it's just a matter of like how much, it's kind of just an open question. I mean, it's a similar question to how do you decide when you're done outside of AutoML too? Like how much time do you put into it? When do you decide that a model is good enough? I think you apply those same you know, decisions or thinking around AutoML tools. But generally what we've seen is that you can get pretty good results in like an hour on most data sets. And if you want to run it for longer, you can. But I think I would, yeah, there's not really a real answer to that, because it's also a combination of like what kind of machine are you running it on? And so if you're running it on a laptop, it might take a long time. If you're running it on like a high-powered instance on Amazon, EC2 or something like that, it might be shorter. So there's really not a good solution or response to that, other than just see if it feels good enough to you, and then if it's not, keep going.
Thank you. So I have a question about explainable AI. Is there any way to plot Shapley values after fitting out in H2O after using R for H2O for H2O modeling?
Yeah, there is for tree-based models, there is. So that would be something where if you go to the H2O user guide and, well, actually that's not true because yesterday I filed a ticket that there wasn't something in the user guide about this and that we're gonna add it, I think. But if you Google Shapley and H2O, or specifically TreeShap, TREESHAP, you'll see, you'll find a blog post. Every time we do a new release of H2O, we write a blog post highlighting some of the good features or the exciting new features. And then you'll see in that blog post a link to a demo notebook. I can't remember if it's in R or Python, but if it's not in R, we probably were going to write one soon. I know when we add the page to the user guide, this is relatively new in H2O, that's why it's not there yet. But yeah, the answer is yes. I'm just trying to rack my brain for what are the best resources to point you to, but I can also try to follow up offline with a script or something like that.
Thank you very much. We'll be happy to put the script in the description of the talk. And the very last question. So Auto ML implies also a bit of auto feature engineering. Are there any ways to automatically pre-process text data with H2O Auto ML?
There's not an automatic way right now. That's one of our open tickets on our roadmap is to process text data raw. And so we can do that because we have in H2O, we have a word-to-vec implementation. So our plan is right now you can just do it outside of Auto ML. You train a word-to-vec model or import a word-to-vec model and convert your text into numbers, and then you pass that on to Auto ML. That's a simple thing that we can wrap inside of the function. We just haven't done it yet, but that would be how we would do it.
Thank you. And to wrap up this Q&A session, we have a very last question about Our Ladies. What are the plans of Our Ladies for next years, and how Our Ladies plan to adapt to the COVID situation?
Let's see. Well, our long-term plan is just world domination. I'm just kidding. Sort of. That was a joke. So yeah, I mean, we don't have any specific plans. What happens now is that generally people know about Our Ladies. So new chapters are opening up. People come to us if they want to open up a chapter. So we don't have any necessarily plans around that other than just keep doing what we're doing. But for online meetups, we have been switching all of the Our Ladies meetups to online meetups. And so we now have like an Our Ladies Zoom account. And so chapters can sign up and organize webinars. And we're trying to also record a lot of the talks. So I think in the past, probably most Our Ladies events didn't get recorded, or if they did, we didn't have that organized in any way. So one of the things that we're doing right now is trying to encourage people to record, and it's easy to do that with Zoom or any other broadcasting software. And we now do have an Our Ladies YouTube channel. I can give you a link to that as well. So you'll start to see that we have lots of meetups getting recorded, so you can watch them anytime. And then we're also seeing like it's nice to have to sort of attend an Our Ladies meetup on some other place in the world. And so now we have a lot more interconnection between our chapters because people are able to show up at an Our Ladies meetup anywhere and meet new people. And so we would encourage people to check out our calendar. And sometimes people ask, like, are people who are not women allowed or welcome at Our Ladies meetups? And the answer is always as long as you support our mission and our code of conduct, then of course. So we can also see that maybe lots of people could become introduced to Our Ladies during this time just by being able to attend online meetups. So we would love to have people join.
Thank you. We'll of course put the link to the Our Ladies YouTube channel in the video description, also to your webpage. But I'm almost certain, I'm almost positive that everyone in our audience already knows the address. So just to add a few words from me as a representative of the whyr Foundation. Our foundation deeply treasures and shares the value of diversity in data science promoted by Our Ladies. It's really amazing, and we fully appreciate this effort. And to support it as much as we can, 2 years ago we established a whyr supporting grant for women in data science. And today I have a pleasure and privilege of announcing the 3rd edition of the supporting grant. Also, and in this video description, we'll post a few details about how to apply for the scholarship. And just to sum up, it was a very interesting 60 minutes and a great voyage in the world of the AutoML. Erin, thank you very much for being with us, for giving this webinar. It's really a great pleasure for us for hosting you. It was amazing, and also deep thanks to our audience. Thank you for being here, and thank you for being here with us. Have a good night, at least in my time zone. Bye bye.
Thanks.
Oh, Erin.